Okay, good afternoon. Let's do a problem. How to make this hydrocarbon from building blocks 4 carbons or less. Now, there are many, many solutions to this. I'll just pick one because it's apropos what we discussed last week. But you can think of, and this is too loud, you can think of an analysis of this in a variety of ways. First of all, it's a hydrocarbon. You need functionality. So we do the old trick of retrosynthetically. We put in the function that we want, where we want it, for a scheme that might be useful. You may not see this at first. So on the back of the pages, you would put in a carbonyl, put in a CC double bond, a triple bond, what have you, at various places until you see something that looks like it might be workable. Secondly, it's worthwhile analyzing what you have here. This is a 10-carbon piece, and you're supposed to use 4 carbon units or less. So you definitely have to break up the molecule. Secondly, it's a ring. So whenever you see a 6-membered ring of cyclohexane, think of ring-forming reactions that you know of that make functionalized 6-membered rings. And as far as I remember, you have 3 now. One is the Diels-Alder reaction. The second one is the electrocyclic ring closure of a hexatrine. And the third is the intramolecular aldol, or mica, followed by intramolecular aldol, which is the Robinson annihilation. Okay, so that's just a variant of the intramolecular aldol. So there are 3 ways of actually thinking about this and then putting in functionality that allows you to unravel the ring. So Diels-Alder is particularly, actually Diels-Alder and electrocyclic closures, they are quite useful retrosynthetically because you can cleave in various ways. In the Diels-Alder reaction, you can think of cleaving these 2 bonds. This would be the dienophilic part, the dienophile, but this would be a double bond that would be coming in. Notice that this would be electron-rich, but you just put in a carbonyl in here since we can get rid of it. That makes it an electron-poor ene, and we would have a diene that would be composed of these pieces. And you can think about building up that diene from smaller pieces by using the chemistry that you know. Elimination chemistry to put in double bonds of Wittig reaction would be particularly actually easy here. But that's just one way, cleaving here. You can keep on moving. You can cleave here. That would give you an ethylene and this diene. Or you can cleave here, ethylene and this diene. Or here, you see, get the picture? You can go around 6 times and cleave until you find a combination that looks manageable and also ideally, and that's where you can pre-select, a combination where you are cleaving pieces such that you get equally sized fragments. So that's one possibility. Hexatrine ring closure is the same kind of thing. Okay, so you would have to put in 2 double bonds here that you can hydrogenate off in the last step, and then retrosynthetically cleave in the ring opening, the reverse ring closure, at various places. You can do that again in 6 possible ways. So think about how this might work. Okay? The solution I'm giving, and there may be other ways of doing this. You're now in command of sufficient synthetic chemistry that you can put this together in many different ways. The way I'm going to unravel this is to think of this as a cyclohexenone because there are substituents that we have to put in, and to retrosynthetically take away the substituents always breaks carbon-carbon bonds, and you always get smaller fragments. So I'm just choosing this simply to review some of the chemistry we discussed last week. So I'm putting in the carbonyl here. And now with the carbonyl here, you know how to cleave this and that, one of these, and the ethyl, because we know how to put them in by initially on a cyclohexenone. So let me write the precursor. By initially coming in with a cuprate that generates an enolate anion, and then you alkylate. Okay? And that gives you exactly this structure here. So this is now down to 7 carbons, so that's not bad. Here now you can try a variety of things, but the bottom line that I already addressed earlier on with the alternatives, Diels-Alder and retrocyclization, things like that, you got to open the ring somehow, cleave it in some way, because the restriction is 4 carbons or less. Okay? So I'm going to do it by retrosynthetically ring open this to an acyclic system, and we have many more possibilities of dealing with stitching together acyclic systems using 3A chemistry as well as all the chemistry we learned here. And so the way to cleave that is the retroaldol. And the retroaldol gives you, and I'm lining up the carbons the way they unravel, gives you this, okay? Because the intramolecular aldol condensation will give you that double bond. And now if you stare at this long enough, it's a 1, 2, 3, 4, 5 dicarbonyl arrangement that is 2 carbonyl functions of aldehydes or ketones, in this case aldehydes, that are separated by only 3 carbons, and those are made by the Michael addition. And this is symmetrical, so we don't have a problem with asymmetry and therefore various choices. And so I'm going to cleave here in the retromichael sense, which gives you as the starting material acetone and this alpha-beta unsaturated enone, butenone. Okay? And we're there. The problem is solved. Okay? Now, the beauty of this approach is it's very, very fast because it's basically 3 steps. The first step is the intramolecular aldol, the intermolecular aldol condensation of the enolate, not the aldol, the Michael addition of the enolate onto the beta carbon of this enone that generates this guy. If you do it at low temperature, it'll stop there. We'll just do it at high temperatures, followed by cyclization. That's the Robinson annihilation. Okay? 1 step to this. Then introducing the methyl through cuprate and enolate alkylation chemistry is another 1 pot. It's 2 steps, but it's in the same pot. That gives you this guy. And finally, we remove the carbonyl using any one of the 3 methods you know. One is Clemmensen reduction, that's zinc HCl, zinc amalgam HCl. Wolff-Kishner reduction, hydrazine plus sodium hydroxide base, and heat. And the third one is making a thioacetal and then treat it with nickel. Okay. The question here? Yeah.
I was wondering with the Robinson annihilation, without the equalate, do not undergo the intramolecular...
Well, you have to warm it up a little bit.
Okay. Will you get the alcohol out in that case?
That's an interview. You probably get some alcohol. It depends on the temperature.
Okay.
But typically people don't stop because they want this to final cyclized product. So as an exercise, try and unravel this molecule anyway, the product molecule any way you can. And it doesn't matter if you actually don't get a solution that's viable. It's the exercise of doing it, thinking of the molecule as a piece to cleave according to some chemistry that you know. And you sometimes may only get to 1 or 2 steps and you realize, oh, that's hopeless. Okay, but you went through the thought process, and that's extremely useful when it comes to analyzing problems that will be easier than this in an exam. Okay. Okay, we ended somewhat haphazardly last week with the preparation of carbonyl, so I'll restart basically. There are 4 general ways. 2 of them are shown here under point 1, and that's the oxidation of primary alcohols and aldehydes. Okay, so we know that primary alcohols with chromium-6 in aqueous solution, through the formation of the aldehyde that makes the hydrate, they go on all the way to the carboxylic acid, which of course means that you can also start with any aldehyde. All aldehydes will oxidize to the corresponding carboxylic acid. So this is chemistry that we already know. And then we mentioned a neat extension of carbonyl Grignard addition chemistry, namely Grignards add to carbon dioxide. So this is like a super ketone, if you wish. Not a ketone at all, really, but a supercarbonyl that is reactive because both oxygens pull on this carbon, and so alkyl lithiums or Grignards add, they make the corresponding carboxylate, and then you hydrolyze, and you get the carboxylic acid that way. So now, retrosynthetically, you can think of carboxylic acids coming either from primary alcohols, which in turn, of course, you can build up by using chapter 8 Grignard chemistry, or you can think of it as coming from a Grignard, which ultimately is a haloalkane. The haloalkane can be traced all the way back to a hydrocarbon. So you're starting to get a feel for why petroleum products are feedstocks for the chemical industry. These are all hydrocarbons, and the chemical industry uses processes like this to add value to these hydrocarbons by functionalizing them and then turning them into more and more valuable commodities. And the third one that we looked at very briefly was cyanide displacement to give you these cyanides or nitriles, and nitriles can be hydrolyzed. Okay? They can be hydrolyzed with acid or with base. Here I'm showing you base, and they give carboxylic acid. So this is some, we'll discuss the mechanism in the next chapter, but you can see that actually the nitrogen is blown off. It comes off as ammonia, or if you're doing an acid catalyzed hydrolysis, it's ammonium, it formally, and so I've doctored my slide last night a little bit, formally, topologically, amounts to a triple hydration of the C and triple bond. So you can see that the C and triple bond should be polarized, delta plus on carbon, delta minus on nitrogen, and water, of course, is polarized this way, and you add this 3 times. So you add 3 hydroxys to this carbon and 3 protons to the nitrogen, and that gives you ammonia, and this trihydroxycarbon. Compounds like this are not stable. They're nothing else but hydrates of the corresponding carboxylic acid. So this is not the mechanism, but topologically, this is the way it goes. Actually, the mechanism in the first step is exactly this hydration, and then it takes a slightly different path that we will address in a minute now. Okay, so here again, you can trace this back to a nitrile. Nitriles can be traced back to haloalkanes. Haloalkanes can be traced back to hydrocarbons. So here's an example. You take this benzene-derived nitrile, common name benzonitrile. Sodium hydroxide gives you this carboxylic acid quantitative. One of the great users of this is to start with an aldehyde or ketone, and then add HCN, so you get the corresponding hydroxynitriles, a reaction that we have discussed in connection with carbonyl chemistry. And at the time, we didn't really know what to do with these guys. Okay, so there's one application. The nitrite turns out to be a very useful functional group, which we'll discuss to a greater extent in the next chapter. But here's one application: you can hydrolyze with the corresponding carboxylic acid. And what follows in this chapter is what we can do with carboxylic acid. So it broadens the scope of your synthetic capability. Functionalizing a carboxylic acid at the alpha position is very important. There are many natural products that contain functions here. Among the most important ones are the ones where we have an amino group here. These are the natural amino acids that build up peptides that make up our body. Okay, so let's look at reactions. And the reaction of carboxylic acids is basically the conversion of the carboxylic acid into so-called derivatives, which are mainly divided into 4 classes. One class is called the acyl halides. We've seen those before, the alkanoyl halides, that we've used them in the Friedel-Crafts chemistry. Then anhydrides, we've seen those a couple of times, including in Friedel-Crafts chemistry. Literally, anhydride means loss of water. Literally, you take 2 carboxylic acids and blow out water. Then come the esters, and then the amides. And notice they all have in common that what you've done is you've replaced the OH function of the carboxylic acid with a different group, a group that generically we'll call the leaving group, because all of these groups can potentially leave in the chemistry that is to come. So all of the carboxylic acid derivatives, including the carboxylic acids themselves, can be described generically like this. And their chemistry is governed by the carbonyl function in the initial step, namely nucleophiles attack at the carbonyl carbon, and electrophiles, i.e., for us, protons, will attack on oxygen. And that is exactly the same as in aldehydes and ketones. Totally identical. The only difference now is that we have a leaving group sitting here. So in a subsequent step, that leaving group can be kicked out, such that the nucleophile actually displaces the leaving group. And that's where the value of these derivatives comes in. And that mechanism is called addition-elimination mechanism. Okay, so here is the nucleophilic substitution by addition elimination. Here's our generic carboxylic acid / derivative. And so a nucleophile can come in, kicks out the electron pair, proton comes off, if there is a proton here, and it comes back on the oxygen, so you have the addition product. That's exactly the first step of hydration of aldehydes and ketones, of alcohol addition, hemiaminal formation, hemi acetal formation, amine addition, hemiaminal addition. And in the aldehydes and ketones, typically we stop there. Couldn't get much further, exception being amines, where you could get elimination, either to imines or enamines. Here we can have another option, namely the leaving group can leave. And so this electron pair can kick back in, kick out the leaving group, and that gives you now a substitution by the nucleophile of the L group. So notice, you can't do SN2 reactions on sp2 hybridized carbons, so nature finds a way around it. It first just adds, and then it eliminates, rather than doing direct displacement. This intermediate, because you're starting with sp2, you go sp3, and you go back to sp2, is often colloquially called the tetrahedral intermediate. So if you wanted to do this with L equals hydroxide, as here, one problem is, of course, the nucleophile can act as a base, or complementary view is the carboxylic acid is acidic, and it can protonate nucleophiles, particularly if they're negatively charged, but anything bearing electron pairs potentially can be protonated. So if the nucleophile is a base, such as an amine, then it will protonate and make the carboxylate salt. And that will pull the carboxylic acid into a lower energy configuration, which is the carboxylate. Okay? And in order for a reaction to occur by nucleophilic addition elimination, as we've shown up here, we have to set up this equilibrium. And that means that in order for this guy now to do nucleophilic addition, it has to climb out of the lower lying state here to back to the carboxylic acid and then get over the activation energy for the nucleophilic addition. Meaning it gets very hard, actually. So carboxylic acids have the big problem that they're acidic, and so nucleophiles will deprotonate. And so we'll have to find a way around that. So but again, back to the generic mechanism, there's a base catalyzed mechanism and an acid catalyzed mechanism, and they correspond in the first step completely to what we did with aldehydes and ketones. So it's basically, I'm repeating myself here. So the nucleophile can be deprotonated with some base, or it is itself actually coming in as a negatively charged nucleophile, such as hydroxide, for example. And it comes in and adds O minus, the electron pair gets kicked out, gets O minus, and then it comes back in and kicks out the leaving group. So incredibly facile, sort of like in-out mechanism. Okay? The only slightly more elaborate, because it's two steps, than direct SN2, but because it can't do direct SN2. And if you do this with acid, we do the old thing of protonating first. That activates the carbonyl function, and typically we now come in with a uncharged, lesser nucleophilic nucleophile. That's why we need the activation with acid, and that comes in. Okay, then proton comes off, and then we under acidic conditions, the leaving group is first protonated, and then it leaves, and you get the protonated displacement product, and then you lose the proton. Okay. Very straightforward. So let's see how this pans out in reality for the various carboxylic acid derivatives. So let's start with the acyl halides. The acyl halides turn out to be the most reactive of the carboxylic acid derivatives because we are furthest to the right in the periodic table. The halogens pull the most. Okay? And that means that they're activating this carbonyl carbon the most. How do we make them? Well, in principle, according to the generic scheme that we've written, potentially one could come in with a nucleophile addition elimination, make the acid chloride. But there's several problems with this. One is the halides are very poor nucleophiles. The converse is that the corresponding hydrohalogens, the acids, are very strong acids because the anions are very stable, very happy. Okay? So this guy is very, very sluggish, so it doesn't want to come in. And the problem is that if it were a better nucleophile, frequently it would make it a better base also, and it would start deprotonating the carboxylic acid, taking the carboxylic acid out of the equilibrium picture. That's no good. Okay? Second problem is that this reaction, actually, that you wouldn't have known at this stage. You could have found out by looking up tables of bond strengths. The bonds made are weaker than the sum of the bonds made is weaker than the sum of the bonds lost. And so it's uphill. And if thermodynamics is against you, you have to throw the towel. There's no way around it. Okay? So this is less stable than that. And there's not only a thermodynamic problem that this is actually the equilibrium lies to the left, but there is also an activation energy problem, not only because this is a poor nucleophile, but also because the hydroxide is a very poor leaving group, as we have learned over and over again, with some exceptions. We now know two exceptions. They were very special, but there was a negative charge that was basically kicking out the hydroxide because it was proximal. Okay? So that's not the way to go. The solution to that is to use inorganic reagents, particularly these three are the most popular, that hopefully look familiar to you, because these are the reagents we've used in Chapter 9 to turn alcohols into haloalkanes. There we had a similar problem, or related problem. Hydroxide is a very poor leaving group. We can't just come in with a halide and kick out hydroxide. So what we did was we improved the leaving power of the hydroxy leaving group by turning it into a better leaving group. And we use these reagents as auxiliaries. The exactly same thing works for carboxylic acids. So in this function, topologically at least, you can view carboxylic acids, the hydroxy in carboxylic acid, as an alcohol OH, which is displaced by halide using these reagents. While the mechanism is slightly different, although very similar, it's the same but adjusted to the fact that we're dealing not with a normal alcohol, but with a carboxylic acid. And so what happens here is, as in the case of alcohols, it was the OH that attacked the SOCl2 and turned it into this guy. Well, this was an R group down here. And that was an excellent leaving group because it's a sulfuric acid type derivative. The sulfur pulls and the sulfur oxygen double bond pulls, and this leaving as the anion is great because it's delocalized by resonance. And in fact, it falls apart because it will kick out chloride in the process. Here, we have to attack a carboxylic acid. And remember, electrophiles attack carboxylic acids not at the OH. They attack it at the carbonyl. So it's a mechanistic twist, which in the end is irrelevant because you get the same product. It's so similar to protonation of the carboxylic acid occurs at this oxygen. And once you protonate here, you get the dihydroxycarbocalin. It's symmetrical. So both oxygens become equivalent in this case. So here, we attack with this oxygen over here to pick out the chloride. And remember, the reason for this, of course, is resonance. Attacking with electrophiles here allows you to write a carbocalin here that has another resonance form with the electron pair at the bottom kicking in, an octet structure. So when you do this, you come in and kick out chloride. This is by addition elimination. Also, you get this beast here, and I've written this resonance form. Just for fun, you could have written the resonance form with a plus charge here and oxygen neutral. And then this loses proton, and now we have turned the carboxylic acid into one in which one of the oxygens is now an excellent leaving group. Notice that this is topologically essentially the same as this OH having attacked.